This chapter is about subgroups. Given a group G, a subgroup is a non-empty subset that's a group under the operation from G. We have special notation for this. We use the less than or equal sign to say that S is a subgroup of G. Now, every time we define a subalgebra, given whatever our algebra is, we expect one of the next things that we get is the subbla theorem, which is how do we more quickly check that something is a subbla than verifying all of the axioms. In this case, because a group has so few axioms, there really isn't a shorter test. The only thing we don't have to check for is the identity being in there, because if we check for inverses, we'll automatically get the identity as long as we have closure. But if our subgroup is finite, and here you should be thinking about Galois groups because those are finite groups, so any subset that we take is going to be finite, then all we really need to check is that we have non-empty and closed under our operation. So that's non-empty and G1 holds. And that's kind of nice. There's a quick proof of that here if you want to see what's going on, but really it's that eventually, if there are only finitely many elements and we're closed under multiplication, one of those elements has to be the inverse of the other from the group. Let's look at some examples of subgroups and some non-examples of subgroups. All right, first let's look at the non-negative integers. Notice that this is not a finite subset of the integers, and so we're going to have to use the longer proposition. We can't just check that it's closed under multiplication. We've also got to check for inverses. Now, the operation on the integers is addition because it's a ring, and we know that a group, or a ring under its addition forms an abelian group. We know it's not multiplication here because we didn't throw out 0, so we can't be talking about multiplication. Anyway, we know that 0 is in this set, so it's not empty. We know that the sum of positive integers is a positive integer, so it's closed under addition, but we don't have negative numbers, and so we won't have inverses. So nope, not a subgroup. Now let's look at the even integers. And again, the set of even integers is also infinite, so again, we're going to have to check for inverses, closure, and non-empty. Well, 0's in here because 0 is even. It's not, so that's not empty. The sum of even integers is still even, and so it's closed under addition. And the additive inverse of an even number is also even, so we've got additive inverses in here, and therefore the even integers form a subgroup of the integers. And I just want to point something out because we're getting closer to the end of the semester when we should be wrapping things up and drawing big connections. There's another way that we can write the even integers, and that is as a principal ideal. So this set E here, we've seen it in a couple ways. We've seen it written as 2z, and we've also seen it written as the principal ideal generated by 2. So principal ideals in the integers are always going to be additive subgroups because they're closed under addition and they're closed under multiplication by -1. So this is a whole bunch of sets we've already thought about that we can write as subgroups. In fact, that's even true of subrings because subrings are going to satisfy A1 through A5 for our ring, and so they will also be subgroups, additive subgroups. The next example is a little bit different. We're taking the real numbers 1 and -1, and we're thinking of the group operation as multiplication of real numbers. This is a finite subset of the group of non-zero real numbers under multiplication, so we just need to make sure that it's non-empty. Well, great, we see two things are in it, so S is not empty. And we need to check that it's closed under multiplication, and that's what this table is doing. So this is showing closure. So we've got that this is a subgroup. Woo! Now, when we're working with a subgroup of a permutation group, the good news is our permutation groups that we're considering are finite, and so a subset of a permutation group will be finite, and so we only need to check that it's non-empty and that it's closed under multiplication, and that's what the last example on this page does. So you see the multiplication table, and it's showing that when I multiply the identity 1, 2, 3, or 1, 3, 2 all together, I get elements from that same subset back, and therefore this is a subgroup of S3. Why are we talking about all of this? Well, we want to work with our Galois groups, and we want to tie the idea of a Galois group and a subgroup of a Galois group to a field and an extension of that field. Now that sounds a little funny because subgroups are sub-things, and extension fields, that relationship goes the other way. But we see that the Galois group is called an inclusion reversing relationship, or an inclusion reversing functor, if you want to get really fancy. So let's think a little bit more about this example. So let's start with a sequence of fields. We've got F contained in L contained in E. And I want to think about the automorphisms from E to itself that fix L and from E to itself that fix F. And I want to think about the way those automorphisms are related. So I'm going to let F be an automorphism in the Galois group of E over L, and I'm going to let G be an automorphism in the Galois group of E over F. And I claim that F is also an element of the Galois group of E over F. And if I can show that, that will show the containment argument to show that the Galois group of E over L is a subset of the Galois group of E over F. And then we can worry about whether or not it's a subgroup. Well, we already know that F from E to E is an automorphism of the field E to itself. And so now the only question is, does it fix F? That means that F of A is A for every element A in L. But F is a subset of L, so F of A equals A for all A and F, and therefore F fixes big F. And that means that F is an element of the Galois group of E over F. Okay, cool. So that means that we have a subset, and now our question is whether or not it's a subgroup. Well, because we're trying to prove something in general, I will use the definition of a subgroup. I know that the identity automorphism is in the Galois group of E over L, so it's not empty. I also know that it itself is a group under function composition, which is the same operation as in the group Galois group of E over F. And therefore, it is a subgroup. So this tells us that the Galois groups of a big top field that we're interested over different base fields as we work up an extension of fields chain will give us a sequence of subgroups. And that's pretty useful to us. We'll see later how we're going to use that. Now the last thing on this page is a proposition that tells us that given a group G, it has two automatic subgroups. The set containing only the identity and the the group itself is a subgroup. And so we call those trivial subgroups since every group has them. On this page, we get a little bit of information about properties of group homomorphisms. That is, that the identity gets mapped to the identity and inverses get mapped to inverses. We also get the definition of the kernel and image of a group homomorphism. The kernel is everything that gets sent to the identity in the codomain, and the image is everything in the codomain that you can reach by plugging in something from the domain into the homomorphism. It turns out that the kernel and the image of a group homomorphism are each a subgroup of the group they belong to. So the kernel is a subgroup of the domain, and the image is a subgroup of the codomain. And there's a short proof of that below. Something we'll discover later is that the kernel is a little bit more special. And I want to remind you of what we know about ring homomorphisms. If we think about the kernel of a ring homomorphism, we proved that it's a subring, but we proved even more. We proved that it's an ideal, which is like a really special kind of subring that has this extra strong multiplication property. We're going to get a certain type of subgroup that's like an extra special, really good subgroup as well. And later on, we'll be able to show that the kernel of a group homomorphism is that super awesome, really great special type of subgroup. The very last result in the set of notes here is that if we take a polynomial that has n distinct roots, then it's the Galois group of f adjoin the roots of p of x over f is isomorphic to a subgroup of Sn, and we use that isomorphism T that we developed before. The way that an isomorphism functions for us is it really just lets us say, oh, we've got a Galois group, let's just think about it as a subgroup of permutations belonging to Sn, work with the permutations, and we can be confident that the algebra will map back to our Galois group and the elements the way we originally wrote them down. That's all we've got to say today about subgroups. Soon we'll talk about how do we make subgroups, that is, how do we find special elements of the subgroup that let us write it down concisely. Then we'll talk about certain really special kinds of subgroups, and then we'll start to wrap up the course and figure out how to use these Galois groups and subgroups of Galois groups to figure out why there's no quintic formula. So until next time, stay safe and stay healthy.